Hello everyone, I'm G. Sagastan from the Database Exploration Lab at the University of Texas at Arlington, along with Suraj and Professor Gautam Das. This work was done in close collaboration with Muhammad and Professor Sanjudeep Basu Roy from the Big Data Analytics Lab at New Jersey Institute of Technology. The title for the talk is A Generalized Approach for Reducing Expensive Distance Calls for a Broad Class of Proximity Problems. There are numerous companies in the internet giants who try to solve these proximity problems on a day-to-day basis. Companies like Google, Microsoft, DuckDuckGo, StartPage. These companies try to find objects or documents which are as closer to the query which is presented to them. Another example is the reverse images, where the task is to find out images or set of images which is as closer to the query image which is presented to the query engine like Google, Bing, and Yahoo. Along these lines, it finds numerous applications in medical field, such as comparison of fMRI scans, comparison of CAT scans for the disease diagnostics. The overall aim of this paper is to reduce the total number of expensive distance oracles at the expense of local computation for completing the proximity problems. For this purpose, we closely analyzed all of the proximity problems in order to see where the distance oracle calls come from. And we understand that all of these calls come from the if statements, whether to decide whether a particular edge that needs to be added to a part of the solution framework. For example, if it's k nearest neighbor, we really wanted to know if the new edge is really closer than the k neighbors that it already has. To reduce the number of distance calls, we have a linear programming based solution framework called direct feasibility test, which represents these edges as variables and add triangle inequalities in order to solve this for the feasibility region, which can avoid distance computations explicitly. Direct feasibility test is a novel formulation of the problem. It forms a system of linear equations, equations for variables in the order of n square, equations for triangle equals in the order of n cube. Off-the-shelf linear programming solvers can be used, but it's expensive, so thus it can be used only for small scale graph and then our scales for graphs which are medium or large size. So we now start looking at algorithms which can solve these kind of settings. Thus, in reality, we reauthor the proximity algorithms in order to avoid distance computations by replacing them with lower bound and the upper bound computations, avoiding the explicit oracle calls. And how do we do it? We will explain them in the paper and in the talk. So instead of a cubic algorithm, now we have an order of m plus n log n algorithm, which scales very well to medium to large size graphs, but does not scale very well for the very large graph settings. Thus, to scale to very large settings, we started taking a trade-off between the exact lower bound and upper bound in order to produce more looser bounds. Thus, we unlocked the powerful large graph settings using a triangulation method. All the algorithms which are discussed in our paper, including the exact and the approximate LBUB computation, produce the exact same answer which are produced by the original proximity algorithm. We tested our results on the real-life datasets, and you can see the results in the following slides. In the portfolio, you can see the lower bounds produced by the ADM and SPLUB are exactly the same, which is the same case for the upper bounds. The tri-scheme lower bound, which is the approximate lower bound, is much better than the T-laser lower bounds and the laser lower bounds, as you can see from these pictures. Let us take a quick look at the answers for the PRIMS algorithm. So you can see that the ADM takes a very large amount of time, and SPLUB takes a fraction of the time that is required by the ADM, and tri-scheme is blazingly fast. You can not even see in these graphs. Here is the glimpse of the distance save that we obtained using PRIMS algorithm. Here you can see multiple fields. We would like you to take a look at only the two fields which are given the last four columns: the laser, the save, the T-laser, and the save. So you can see that as the scale increases, your distance save ups go up, and it is incredibly doing very well against laser and T-laser in the order of 63 to 51%, and even the 63% is in the order of millions of distance calls. There's much more than what we have discussed so far in our paper. More results, more detailed results from various proximity algorithms, drawbacks of competitive algorithms, proof of concept results from direct feasibility tests, scalability experiments, computational challenges, response to varying parameters in proximity algorithms. Please have a look at the paper. Thank you so much.